Okay. So today's agenda is moving on to another class of algorithms, which is called function approximation based RL. And we'll also implement tabular TD0 algorithm. I thought I'll do it at the end of the class. It's not going to be a long one. So we'll do it at the end instead of doing it at the beginning so that we can have some time on the code. So what I'll try to do today is till now, what did we see? So we saw till today, but we saw that the state space S was fully known, right? Fully known. It was countable, small and finite. Small and finite means countable, but yeah. So you could write out now, you could have written down a table like this, a state one, what was your value function, what is your action, and so on, right? State two and dot 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 state n. Your value function is v of one, v of two, and v of n. Similarly, your action could be pi of one, pi of n, isn't it? You could have done this. So you could have written down a table, and this would have given you a map from the state to the value function for all the algorithms that we discussed. Because we saw that the value function is defined as a state to real number definition for a policy pi. So any questions? So I think you recall all this. So we did all the learning, be the TD, lambda learning, Q learning, SARSA algorithms using this table form. So if it was your Q and state comma action function, so A1, A2 dot 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 AK and S1 dot 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 SN, you still had a table which each of them give you K of SI comma AG. Right. So this is what we had been doing, but there is a problem with this. There is a shortcoming for these algorithms, for these tabular algorithms. So what are the shortcomings? So once your state space becomes infinite or uncountable or even very large and so on, let's consider the case where it's very large. So for example, you have S1, S2 dot 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 Sn, say you have a million 10 to the power 10 states, right? So in this case, the representation of these states, like whatever you want to learn the value function, you have to store all of these states in the memory. You cannot really do things which are like you have to access all the states at a particular time. Basically, you cannot, like for 10 to the power 10 states, if you have to find some transition probability matrix, so that will be like S1, S2, and that will be like 10 to the power 10 squared, so 10 to the power 20, right? So if n is large, is very, very high, the probability distributions would be this would be difficult to store. Similarly, storing v pi of s and all the pi policies of s is going to be like a cumbersome procedure. So why will it happen? Because think of it that states as a one-hot encoding, where the first representation, or it is the ith element of this row is 1, rest are all zeros. So that can be used to represent a state. So you have a diagonal matrix. So you end up having a lot of redundancy. This is, we'll see why am I telling this, but you have a lot of space constraints. And similarly, v pi of s, if s is in some real numbers, the state space Rn, then you're gone. You're doomed. You cannot put a countable set, isn't it? Do you agree? You cannot put it on a table. 1, 2, dot, 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 n won't work. Do you agree?
Yes.
Any questions? Okay. So if you don't have any questions, so can you tell me what could be one of the ways I can represent these states? Could there be a procedure I can use to represent these states? So the states, each of the states could be represented using features, right? So then we tell that each of the feature could represent the particular state, isn't it? Right? For example, the 0, 0, 0, 1, 0, 0, 0, 0. This is the, say, the ith state. This would represent the state Si. Correct? If this is the ith column is ith element is 1. Similarly, this is the most naive way of representing a state. But what I'm trying to say is, can we represent a state using much compact definitions? Like, for example, temperature of a Bunsen burner. If you have a furnace, if you have a furnace in a in a chemical industry, you could use temperature as a state, which is a real number again. And you can take decisions on how to decrease or increase temperature. But we'll see what to do for that. So what I mean to say is, if you have very, very large state spaces, and if they are, for example, continuous in nature, then you often end up, the tabular methods won't work for you to determine whatever is the value function. Okay, so let us take an example to understand this. So for example, if you are cycling, if you're learning an agent to do cycling, so the cycle could be represented as few parameters, right? You could represent it as the velocity, which could itself be a velocity along x and y. You have an acceleration parameter, you have an angular velocity, and you have an angular acceleration, alpha, right? I think this can represent all the possible states of a cycle, right? So if you're going too fast, and if you're like on a very, very sharp turn and you're going too fast, and the friction does not allow you to go that fast. Sorry, again. So if the friction does not allow you to go that fast, then what do? You just, so you say that you slow down. Slow down if you are fast on a turn, right? So for example, so now look at this, each of these components. So if I had to, so each of them are positive or negative real numbers, right? So your state space would be r to the power 4, isn't it? Your states would belong, each state would belong in r to the power 4, isn't it?
Yes. Yes.
So now this is an uncountable set. Uncountable set. So you cannot put all the states down, right? You cannot say S1, S2, or dot 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 S infinity. You cannot do that. You cannot put a table. No tables will be allowed. No tables could be formed. So instead, so you see these are all real numbers. So instead, we'll have to devise a method in which we can approximate the value function and all, or do all of the states, actions, and everything based on, for example, based on some functions, right? So if I have a function that takes in the state S and returns a real number directly, then I am done, right? I will not be having to store the value of every state, all the infinite number of states. Do you agree? If I have a function that maps from R to R, or R to the power n to R, then that is done. Do you agree? So for example, if they say there are D features, right? Initially, this was S state space, which was finite. But now it is either very large or this it could actually belong to all of these D features. Like each of these D features could be R. That's the big goal of the things that we'll be doing. That is linear function approximation. So or any approximation, function approximation for that matter. So let us try to understand. So and here, for example, your actions would be the force applied and the torque you would apply to change your velocity and angular momentum. So and similarly, your reward could be if you fall down, you could get a negative reward, and your the same way you could keep going. That's the idea. Is it clear to everyone? So why the state space of tables is not possible? Is there a
Yes.
question? Okay. So I'll give you a concrete example of how to form this state space. And then we'll try to get. So this is inspired from this Sutton and Bartow example. So where you say that you have a self-driving car company. You have a self-driving car company in Kolkata, and then what do they do? They lend their cars for rent at two locations, say at Boranagar and at Jadavpur. So anyone who rents a car, they rent it for rupees R for an hour, maybe R per hour maybe, and people can take the car from any of the location and deposit it at any other location by 12 midnight. After midnight, the employees are told to collect the car from the location, one location to the other at rupees C per delivery. So we have to, what you have to do is the end goal is this, which we'll come to later on. That is finding the optimal strategy. That is how many cars to transfer. That is the goal, end goal. But what is the intermediate idea? That is, we have to understand what the states could be. How could we represent each of the states? Similarly, the actions could be moving the vehicles from one to another. And now we have a few questions. We have to define a formula for the state, right? And then we have to define a state space matrix with that. So let us try to do that. So what do I say? I have, and we have been told, say total number of cars is, it has been told is 4. Total cars is equal to 4. So, and you have, so this is say Boranagar, this is Jadavpur. And you have to pick up cars from one side and drop to another. So at a current moment, say at midnight, you have 3 cars in Varanagar and 1 at Jadavpur. So what is the action would be number of cars to transfer from one to another. So this is which side would you transfer is the question. Is the action that you want to select. Say in how many you want to transfer. But for the time being, we are only considering the states. So every state, the states could be defined by the states for one of them. So you could always define this by one of the numbers, but let us define it this way. Number of cars at Boranagar and number of cars at Jadavpur. Okay. So when we have these two together, do you agree will represent all possible states? Yes or no? Will represent each of the all possible states. Fine. Any questions? For example, at a particular time, say state 1, you have 4 cars all in Boranagar and 0 car in Jadavpur. Similarly, 3 cars in Boranagar, 1 in Jadavpur, 2 cars in 2, 3, 1, and 0, 1, 3, sorry, and 0, 4. So this is state 2, this is state 3, this is state 4, and this is state 5. Do you agree? These are all the possible states that we have. This is just an example. This is still a countable small set. We could have done something like this, where we could have represented state 1 as this 1, 0, 0, 0, 0. S2 as 0, 1, 0, 0, 0. S3 as 0, 0, 1, 0, 0. S4 as 0, 0, 0, 1, 0. S5 as 0, 0, 0, 0, 1. So we could have represent the states like this as well. But you see, in this you have 25 n squared number of parameters, but here you just have n into 2. Right? For let 2 be the number of features. This is the number of features that we have. So is this clear? So instead of having all these numbers to represent a state, which is again unreal, not required at all. This is in the case of tabular, you do this, that you have one number, each state having a unique indicator, whatever you like to call it. Similarly, in this state, you just have two numbers, that is 4, 0, 3, 1. They are representing the number of cars in each of these two locations, and each of them totally represent one state. Do you agree? At a particular time, when there are 3 cars in B, there can only be 1 car in G. Do you agree? There are no other cases. So what I mean to do now is, so this is what we call as the feature matrix. State and feature matrix. Feature matrix, right? So if this is the state feature matrix, then what would happen? What we want is, using this matrix, we want to learn a W such that V pi we get for every state. So we want to learn. So in this case, what will be the dimension of W? W1 and W2. So this is W1, number of cars at Varanagapur, plus W2, number of cars at Jadavpur. And we say that this is equal to the value function of state of a state. Do you agree? We can do this, right? Using these features, we can learn a value function based on the features. This is called function approximation. Fine. Any questions? This is the goal of our entire session today. So if you have a question, please ask, and then otherwise I'll go into the next. Any questions? Okay, let's see what is function approximation theoretically. Okay, so now we say that since you all saw that we cannot directly always write a value function from the state space to real numbers, we are planning here to write a value function V pi from R to the power D to R. Is this clear? So R to the power D would represent every state would belong to R to the power D. Fine. Even if it is a finite state space. So we will assume even if finite number of states exist, we will learn functions from R to the power D to R. Clear? Any questions? Is there something that's bothering? Otherwise, I'll go into what I'll do. So I will say that, so for VS, so you will have so for a particular state, you will have a feature vector, right? So say F1, F2, say FD, correct? For that state. Let us represent as phi1 of S, phi2 of S, and phi D of S. So for example, in the case of the cycling, this could have been the velocity, acceleration, angular velocity, and the angular acceleration. These 4 things could have been your features. But now, if I have this feature vector, what do I want to do? So this represents, so phi of S uniquely represents state S. Correct? So this matrix uniquely represents one state. So for a state, you will get you'll pass it to the value function phi, and you'll get phi of s. So this gives you a real number approximation of the state. Now what you try to do is you define a function, you define the value function as just the state, the feature matrix, the feature vector times some w, right? So where w could belong in r to the power d, right? So because d features are there, so this is like summation of phi s I wi I equal to 1 to d. Is this clear for everybody? So this is a linear function approximation. Any questions? Combination of, so this is just the linear combination of the features. Combinations of the features to get the value function. Get value function of the corresponding state. Now I'll wait for a moment. Okay, so before even waiting, I'll just say that this could also be similarly done. So phi b pi of s could also be passed through a neural network, because we have done neural networks greatly in last time course. But if you have, say, s features, s belongs to r to the power d, this could be passed through a neural network fw, and this again could give me a value function phi of fw of s. So all these things can be done. These are all approximations that I can use, but we will only consider linear function approximations currently. So because we have not done a lot of neural networks, and all of the theory that we'll be developing for linear functions would hold for non-linear functions as well. At least the algorithms would still be the same. Convergence results won't be there, but yeah. Questions?
Could you just repeat the summation part that you wrote here for the
Okay.
feature vector?
Okay. So say you understood that each state was being mapped to a feature vector. Do you agree? We saw this. This is a velocity, acceleration, angular velocity, and alpha. Do you agree?
Yes.
So say these are feature 1, feature 2, feature 3, and feature 4, which could represent, this represents a state. Okay. That is fine.
Yes.
No? Now I say that how can I learn? So this is the basic of any regression problem or anything. So if you have a set of features f1, f2, f3, f4, what is the target that you want to learn? V pi of s, right? This is your target. And you want to use these as the variables to learn the target. Do you agree?
Yeah.
So what I do is I take a combination of them. I say that the output is linearly related to the inputs. We assume that the output is linearly related to the inputs. So let's take an example. Say your value function for a particular state, if you're going too fast, say velocity is very high. So clearly, if the feature velocity is very high, right, what will happen? You are likely to have a lower value function if velocity is high. Velocity is high, your value function should be low, right? Because it's unsafe for you to travel that way. So what I will do is I will put so W1 could be, say, -1. So as your velocity increases, you become more and more negative. The value function could be. So this will be learned, but I'm just giving an example. Do you agree?
Yeah.
Similarly, you can take combinations of all these. Again, very slow, going very slow as well could be a bad thing. So that way also you could similarly decide what W's to choose. So it could like be something like in terms of so any number. So any number which is here, it's more intuitive to be using -1 because you go faster, you are more likely velocity increases and you are more likely to your value function 2 is likely to decrease. So that's right. So
Could we
just
see this as the row space? I'm just asking. Could we see this
yeah,
as the row
that is.
row
So
space
that's
as
how
well?
we will see. Correct. We will see that's how we'll see it. But currently, what I'm trying to say to you is, why do you do that? Why do you do all of the linear algebra? Is because you want to represent every output as sum of some linear combinations of features, right? That's all we want to do. And we'll see how to do that in row space and things like that. Right? But is the intuition clear? So these features tell me what would tell me that which is good for my state, which is bad for my state. That's all. And I can learn the weights accordingly. Okay.
Yeah, got it.
And the feature
Great.
extraction part may occur in any like traditional way, like in convolution or
Correct.
any kind of traditional way.
So feature extraction could be mixed directly. So we did experiments where you could give the environment to a neural network and the neural network directly outputs the value function. Or you could hand engineer the features as well. That's not a problem. Right? So it's all, you can do it all end to end is the point. Okay, Antariksh?
Yes.
So if you, for some examples, features could just be hand engineered like what we did currently for these two examples. For some examples, it could be just the image of the state. That image itself is a representation. And you could, and the value function could be directly learned. So if you pass it through a neural network, the value function could directly be output of the image. That's the idea. So we'll not go into so complex things as of now, but what we'll try to do is we'll assume whatever data we have, say we have data over say S states, and we'll try to learn the value function for that. That's all we're going to do. So we'll assume, so we want to learn W. So again, recall what is V pi of S is phi transpose S W. That's all we are doing. And phi transpose S W just means, as Shuham was saying, phi 1, phi 2, phi D of S and W1, W2, WD. And if you just take the dot product, you just multiply. It's just a dot product. Phi transpose D means this is the dot product of these two vectors. Just as in your school days, just corresponding coordinates would just be producted out and added, as I showed you. So this is basically phi transpose SI WI, I equal to 1 to T. Okay, so we'll assume for linear function approximation, and we'll try to learn this linear function approximation. And how do we learn it is what we'll try to do now. So again, so this is the linear combination of these W's. So now currently we'll be given a lot of states, say S1, S2, and you can be given say Sn states. So here this matrix is an n cross D matrix. Okay. Do you agree? Phi S1. Correct. And this is the, say this is the ith state, and this is the jth feature. Okay, so all, as Shuham was telling me, I could directly write down the value function of all these states by just multiplying W1, W2, WD. Correct? Yes or no?
Yes.
Okay, so this gives me a flexibility altogether because your n need not, these could just be some examples from the data set. So these need not be specific sets. This could be just n samples of the features, right? And their corresponding value. So you want to predict this value function of that state, correct? Yes or no? So we lose out this entire, we do away with this entire concept of having fixed states because these Sn is just some combination of real numbers. That's what you're going to learn, isn't it? This is your phi matrix. This is all you see in the data. So you could see 10 different velocities, accelerations, and so on. And that's the data that you have. And you want to fit this model W1, WD, which will give you the value function for any combination of the features. Is the intuition getting clear? Are you getting it? So here is just data of the features. Now, we have to learn it. Learn is the value function. Let's see how we'll do that. But currently, can you tell me? So the question is, can you tell me an advantage? Of this method. Some advantage of this method. Can you?
Is finite, isn't it? And that gives me control, and I can see also, as you said,
Exactly.
take the features.
Feature space is finite. This is giving me control. This is flexibility. There's one more control. That is generalizability. Isn't it? So for a tabular matrix, S1, S2, Sn, if you had a tabular data, Sn plus 1, if it is a new state, you are going to fail because this is a question mark in the table. Yes or no? Correct? Do you agree? Not known at all. But for a new state Sn plus 1, here you still have the feature matrix and you can just multiply with W and get your generalized output for the state-based states. Yes or no? Do you agree? Clear?
Yeah.
So this is highly generalizable, which is tabular is not. Okay, so now let's see how to learn these. So you can learn these using similar ideas as regression. So I'm basically going to teach you regression on RL problems. So that's all we're going to learn. So how do we learn? How do we learn W? Is the question. So once we know W, we know the value function for every state. So once we have to learn W, what will I do? So first of all, I know V pi of W or for a state S is phi transpose S W. I know this. So this is the predicted value function. What I want to do is say we know, we don't know actually. We'll see how we learn it in the next class and we'll see a method today as well. But say we know V pi of S. Today we'll assume that we know V pi of S. Then can you tell me there is a way to learn these value function? If I know for every S, if for all S, I already know, I have an oracle to tell me V pi of S, then how can I learn this? So this is basically trying to learn y equal to mx plus c. Your x is given, y is given. That's all you want to learn. How do you learn it? You can simply do least squares. So so what can you do? You can define a loss function over W, saying that it is over all the states S, V pi of S minus phi transpose S into W squared. Yes or no? So what are we trying to do? Say half. We'll see why. Clear? So what is this meaning? So say you have y and say in your school you did all this best fit lines. So actually how do you do a best fit? If people who have done linear regression or linear algebra already know how to do this, but it's basically trying to find a line like this such that this point is mx plus c. And this is for this x comma y, you try to minimize this distance. So you say that this distance, whatever error term you have E, should be minimized. Clear or not? Fine. So if you want to see this again,
I just had a question.
yeah,
So
ahead.
we are using perpendicular least squares, right? Not orthogonal least square.
No, perpendicular least squares. This is the most common form. So you can use all the other point-wise least squares as well, but this is just the. So this is the distance from the y equal to x line. Mx plus c. So this is x comma mx plus c, and this is x comma y. You say that this distance that you have, you get it to be y minus mx plus c. And you say that this should be minimum for all data points. You say that for all data points, this is minimum. So orthogonal least squares and all those are LDA methods. So that those also can be done. So these are something like this. This is what you're telling me, right? We're not
Yeah,
doing that.
and yeah. So we are assuming that there is no error on the x-axis, right? I mean, that's the point
Correct.
of.
Yeah. So you're assuming y is distributed as mx plus some epsilon, where epsilon is so mx plus c plus epsilon, where epsilon is normal 0, 1 or normal c squared. So this is the error term. So this is the model that we fit for. So you minimize the error. This is the Bayesian model. So you can go back and see the machine learning courses that I did. So you were trying to fit a model so that this error term is minimized. So there's no, so this is an independent noise term for every data point, right? As you were saying, there's no noise term correlated with the data. That's it. Okay. Fine.
Yeah, got it.
So we'll try to learn this W. How do we learn this W? We will try to find out, as I was telling you, that the W that minimizes this loss. Let's try to find it out there. Okay. So step one is, I told in this question, is write down a matrix equation for this. First, let me write down the loss. I have already written it. Okay, sorry. I'll copy this. Okay. So what I'll try to do is, let's try and minimize this error. How do I do that? By simple calculus. First, before that, let us write it in terms of the matrix equation. So phi again is the n cross r s cross d matrix, and your W is a vector in RT. And your V pi, say it's a RS matrix. Fine. So you have for every state, you have a value function, V pi of S1, S2, SD, Sn, sorry. Not, yeah, S. Fine, now tell me, how do I do this? So what should I do? First, can I write this as a vector equation? So V pi minus phi W. What would this give me? This would give me V pi of S1 minus phi 1 or phi S1 transpose W, V pi of S2 minus phi S2 times W, and so on till V pi of Sn minus V pi transpose Sn W. Yes or no? Remember, phi is this n cross D matrix and W is D cross 1. Correct? So you get a n cross 1 vector. Yes or no?
Yes.
Yeah.
So this is just the linear combinations of the columns of linear combinations of columns of W of phi with W. That's all I'm going to write. So this is V1, V2, dot, 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 Vn. This is P1, P11, P12, dot, dot, P1n. And so this matrix is there, and then you have W1, dot, 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 Wn. Sorry, Wd. That's it. So that's what is the matrix equation. So I can write it down this way, and then the squares become just, so since these terms are getting squared up, so then what is it? It's just W transpose W, yes or no? If it is, let us represent this as some term delta. So it's just delta times delta, delta transpose delta, yes or no? This is just the square and sum. So just tell me what is W1 squared, W2 squared, dot, 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 WD squared going to be. So W1, where say we represent W equal to W1 dot, 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 WD. This is clearly the sum of squares of the components. This is basically W transpose W, yes or no? This is also called the
Yes.
norm of W.
Yes, L2 norm. Yeah.
Yes.
L2 norm squared. So this is basically your Pythagoras theorem. That's it. Nothing else. The diagonal of the cuboid. Okay. So that's it. So W is this. And so if you're writing it down like W1 dot, 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 WD, this is just, since you're UG student, and just writing it once. So you multiply this with this, and so on. So you end up adding all the W square. So this is fine. So this is what I'm doing, delta times del for delta transpose delta, which is equal to half times the L2 norm of VW. So this is defined as the L2 norm because this is the Euclidean norm, minus V pi phi W. Okay, so this is how we define the loss in terms of a matrix. Now what do we want to do? We want to learn the formula for W star. So let's try and do that. How do you think we should do it? So we'll have to just differentiate. We want to minimize the loss, minimize this loss. So this should be 0 for all Wi's. Yes or no? If you have to minimize this, this has to be an extrema point. Fine. For an extrema, it has to be equal to 0. So let us try and this is a convex function, so it has only a convex function, and this has a minima. So there is no question of a maxima. So only extrema, one extrema exists for a convex function, and we have done it last time as well. But remember, convex function, one extrema, and that is a minima. So all we need to do is we have to take the derivative and set it to 0. So let us take the derivative. V pi of S minus S phi transpose S W I equal to 1 to D squared summation over S. So let's say I take a derivative of the loss for the WG. So what will it is be? Can you tell me? What will this be? The derivative?
It would be W1 times V pi
First,
of S1
okay.
minus phi of S1, phi transpose S1 D1.
J I wrote, no? I equal to 1 to D. I'll just write it as phi transpose SW for the time being. Okay, 2 times this by 2 into the derivative of this function with respect to Wj. Yes or no? Do you agree?
Yes, but for all i's which are not equal to j, it would become
Correct.
0. So only for the corresponding j would the term remain.
Very good. So this term will just be phi s of the jth term. Clear to everyone? So because it's a
Yes.
partial derivative, all other terms will go to 0. Okay, fine. So I'm deriving this for you. You can use it later on when you do regression and things like that. What these are known as matrix calculus results. Matrix calculus results. You can directly write them down, these formulas, once you have derived it, because you will remember. So see, so now I have this as summation of I equal to 1 to n b pi minus phi transpose s w, okay, into phi of s for the j. Correct? So now you see what is the summation over, sorry, s is s equal to 1 to n. So what is the summation over and what is fixed? The summation is over
Feature
the
is
states.
fixed and states is
Yes, feature is fixed, sum over states. Okay, let us see how to do this. So do you agree I can write this term as, let us write this as, so for this state s, phi, okay, phi of s1 for the feature j, phi of s2 for the feature j, and so on, phi of sn for the feature j, okay, into this summation can be written as, this term will be, help me, v pi of s minus phi transpose s into w. Yes or no? V pi of s1 minus phi transpose s1 s2 into w, and so on. V pi of sn minus phi transpose sn into w. Correct? See,
yes.
this with this with this, and so on. So if I fill out this entire matrix, do you agree this is how much? This is your d comma. So there are d features, n states. So I have a d cross n matrix, correct? And this is basically what we have already found out. This, yes or no? That's it. This is just the difference of the value function minus the linear combination of the matrix phi into w. Clear?
Yes.
And this is nothing, this function is nothing but phi transpose, yes or no, this matrix. It's d cross n, and we are writing down the features row wise, which was initially column wise. Correct? So this becomes, so dl dw becomes phi transpose. So in a matrix form, you can write down all the equations in a compressed manner minus phi w. And you can set it to the zero vector. So basically what you do is, this is a formula. So when you have an L2 norm, first of all, an L2 norm of a, say, y minus pw, and you take a derivative with respect to w, you just L2 norm, whatever you have, if you have a norm squared, this basically becomes y minus phi of w, and you get a phi transpose. This is one of the formulas you can remember. Second formula you can remember is, this is your, you can try it as your homework, very simple. So if you have a vector w and you take the L2 norm of that squared, can you tell me what will this be? I'll give you a hint. This is W1 squared, W2 squared, WD squared. And
It's W
differentiating with,
transpose.
yeah, whatever. But what will be the derivative with respect to the vector be for this scalar? This is a scalar value. This is a gradient basically, right? You're doing it in your physics classes everywhere. You're taking a derivative with respect of a scalar with respect to a vector. So you have to take derivative with respect to every component. When you take derivative with respect to one, you get 2 omega 1 or 2 W1. When you take derivative with W2, you get 2 W2. Yes or no? Correct? WD, you get 2 WD. So this is basically 2 times W. Yes or no?
Yes.
Correct?
Yes.
So these things you can sort of try out. I'll give you one more homework today, probably, and that also you can try out. And then you'll see it's very interesting. Right? So you get this vector dLdW equal to 0. So this becomes equal to, so phi transpose b pi minus phi w equal to 0. So now we know that. So we can write this as phi transpose phi transpose phi w is equal to phi transpose v phi. And this is mostly or most likely invertible. Why? Because phi is n cross d, where n should be very, very larger than d, which sort of guarantees that if you have a lot of rows, that it's a full column rank matrix. So these are all little bit of a linear algebra. So if it is a full column rank, when you take phi transpose phi, you end up getting a d cross d matrix, which is a full column rank mostly. So if you have a lot of rows, you have a more likelihood of getting a full column rank. I have done these in details in the ML course. Please, if you want to revise them, you can go and look at them. So you can write this as phi transpose W, V pi. So your W has a closed form solution if V pi is known. If V pi is known. Right? Any questions? Okay. So now for V pi, you can do a scam. You can do some Monte Carlo based estimation for the state. But that is not a good idea, but we'll see how to do this in more formal methods later on. But is this clear? Is this, if V pi was known, we could directly write down the best W. Okay. So, and then once you write it down, your V pi, so it's a bit of a circular thing. We'll see how to solve the circular thing next time. So once you can just write it as this for every state S, right? Even for new states. So now we wrote this down. So now I say that we have a weighted MSE question. What does it mean? So now there's a problem with these formulation that I discussed now. The problem is that according to this objective that I discussed, summation of V pi of S minus phi transpose S into W squared, all states are given equal weightage. Do you agree? Fine. No, any queries? Because you see every state has a 1 multiplied in front of it. So, but this can also happen. It can happen. It can happen that some states are visited more often than others? You remember we discussed in the Markov chain, the stationary distribution of the Markov chain for a policy pi was this, right? Where the distribution for a particular state was the number of times state was visited. Yes or no? If you continue doing traversing the Markov chain n times or whatever m times, this is the same proportion of the times your state I would be in state S. That's what we discussed in the Markov property, right? So therefore, if you have a Markov chain like this, you would be more likely to be in state 1. Yes or no? Clearly, I can see. Okay. So my point is, I would like to, if this is the case, if state 1 is more likely, I would like to have a better estimate of state 1. And this will help us as well. We'll see why when we do Monte Carlo gradient SGDs and so on, we'll see this will help us immensely. Right? Do you agree? You would want a better approximation of state 1 because that's more often you are in that state, correct?
Yes.
Okay. So what I end up doing is I relatively weight the new WMSE loss is we say that say d pi be the invariant distribution or stationary distribution of the states. Be the stationary distribution such that d pi star into v pi, this is the transition matrix, is equal to d mean, d pi, sorry. So this is what we assume. Then we can write this weighted loss as S is equal to 1 to n d mu of S, just weighing the loss squared. Do you agree? And when once I write this, can you tell me what is this equivalent to? You can tell me. This is a very clearly we can see. So first tell me what is this summation of d pi, summation of d pi of S over all S. This is what? D pi is a distribution. Good. This tells me the probability of a state being in for the Markov chain to be in a state S. So this is 1. Summation over all states by law of total probability is 1. So now clearly this is what? If this is a probability of being in state S, and you have a value of corresponding to it, you have a function corresponding to it. What is this?
Expected value.
Expectation.
Very good. Good. So this is the expected value where S is sampled from the mu distribution, the stationary distribution pi transpose SW. So this helps us immensely. Can you tell me why? We'll see, we'll look at this, but when we do the TD learning algorithm with Monte Carlo, but this will help us immensely. Because
We
once
can
we have
use law of large numbers.
yes, we can use law of large numbers just by traversing the stationary distribution, traversing the Markov chain. The Markov chain anyways enforces the stationary distribution if you traverse it long enough, isn't it? We have studied that. So all we need to do is simulate the Markov chain. The Markov chain and use law of large numbers to just take an empirical average of V pi of S minus phi transpose S W squared, where S is sampled based on the stationary distribution. This is basically what you all need to do. We'll do it next time, but basically we'll traverse the Markov chain based on the stationary distribution and then take the empirical average. That's why it is beneficial. So that was a side thing. So for a continuous state space, you could write this as an integral is also a. We're not going to discuss what we'll do for integral state spaces, but we'll assume for the timing that data we have data for it. This is also for continuous analog. Fine. So now we'll try and solve this question. Let's try it. So first part of this question is for weighted MSE. Weighted MSE. Write it as a matrix. Matrix based loss. So L of W is we have seen is d mu V pi of S minus phi transpose S W squared. S is equal to 1 to n. Fine. So we have seen this. Can you tell me how can I write this as a matrix equation? Anyone, any idea? I'll tell you a trick when you have weighted stuff. So normally, what is this? This is just V pi.
We would just multiply D matrix transpose to it.
Good idea, but we have this won't work. That directly, I think, won't work because this becomes a scalar. So once you have this, sorry, this is initially this was V pi of. This was the entire thing, right? For norm squared. For the initial question. This was our value. But now I say that I'll multiply a D matrix in between. This will be a diagonal matrix having D1 of mu, D mu of 1, D mu of 2, D mu of n. Clearly now you see, now it is solved. Why? Because if we take the right hand V pi minus phi W, this is basically what? The linear combination of the rows. So the rows of this matrix becomes multiplied, right? Yes or no? If I multiply D times this, what do I get? This is the what I'll get by row combination as Shoham was telling me. Fine. And now I see these terms are just added. This is one of the ways you can write it.
This looks so similar to the SVD form.
Exactly. This is a quadratic. This is an SVD form. This is a quadratic again. So any quadratic things in an SVD or any place you write it down, they are generally as quadratics. PCAs. This is a weighted quadratic. This is a quadratic equation where you have weights. Weights are given by W. By D, whatever, not W. Fine.
Yeah,
So now
there's the eigenvalues, I think, in the diagonal matrix, the singular values in the SVD.
Correct. So in SVD, you can, so generally what you write it is SVD, be it SVD or eigen decomposition, you can write it as S transpose, S Hermitian, whatever you're writing. In SVD, you will write U transpose V Hermitian and so on. That is also a quadratic decomposition of a matrix. But here, this is just a product of two matrices with linear combinations. Correct? SVD has the same form, but it's a way of finding out. But here we have to find out the SVD. But in this case, we really don't need to find out what anything. This is already given to us. This is an optimization problem to be exact. Right? That's the difference. The form is right as you are telling me. Absolutely right. And also these are matrix decompositions. This is just a scalar. This is a quadratic equation basically. SVDs would give you a matrix at the end of the day, like in terms of orthogonal vectors. They just end up looking the same because it is an outer product. It is an outer product. And this is an inner product. This will give you a scalar. Inner products gives you scalar. So that is dot products. This will give you a scalar value. But this will give you SS transpose is a vector. Even if you have S, these being SS being a vector, this will transpose gives you a 1 cross. For example, this is n cross 1, 1 cross n. This will give you an n cross n matrix. But in this case, this is n cross 1, comma 1 cross n. This is a scalar. Clear?
Yeah.
So fine. So let us write this down. So let us write down the loss again. This we matrix form we wrote. Now let us write down this loss. V pi of S W squared. Again, S is equal to 1 to n. Let's put in half again. Again, DL DJ. What will this be? Yeah, tell me. What will be again? The differentiation is still going to be the same, yes or no?
Yeah, no, again, no. Yeah, no, I mean, all the other terms other than WJ would disappear.
Correct. So this is clearly the same again. So this is again the same, just the W D matrix is multiplied. Yes or no? Do you agree? This is the same thing except the D matrix being multiplied. So we could just write this as, so phi trans, what do we want? We want D mu of, for a particular value of S, D mu of, so say this is summed over all S's, right? S1. So I'll just write down the matrix form. I'll just, there's not much space over here. That's the problem. Okay. I'll write it down here. Okay. Fine, this is available to us. So now I tell you over all the J's. So this is, again, let me write it down. V pi S1 minus phi transpose S1 W, V pi S2 minus phi transpose S2 W, and so on. V pi Sn minus phi transpose Sn W. Do you agree? This is what we have. Fine. And we have this vector corresponding to this. Same way, I'm just writing the same equation. S1 dot 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 phi Sn into d, again pi, this is not mu, d pi of Sn. Correct? Over the same coordinate. Yeah. Fine. Can you tell me now what should I do? How do I decompose this again in two matrices? This I already know. This is V pi minus phi W. The left hand matrix, how do I decompose? See, every row will be this, yes or no? Phi S1 into
We take a diagonal D.
Yeah, I just factorize it and yeah, as he said.
We
good.
take a
You will
diagonal
take a
with all other non-diagonal
Not
zeros.
a diagonal, we can just take out a single vector, D.
no, you cannot do that. You should take a single vector. You cannot write a vector matrix. You cannot write a vector matrix multiplication to get a vector. You require here is a n cross d matrix, right? Or d cross n matrix. That is phi transpose, correct?
No, sorry,
You want it?
I require a total square matrix.
Okay. So phi, you want a d cross n matrix where d features are there. So you see every row has all the d mu's. So basically all you need to do is just multiply d, isn't it? So this is just the linear combinations. So this is phi S1, 1, phi S2, 1. Am I writing it correctly? No, this is phi S2, yeah, phi S2, 1 and phi SN1. And then you're multiplying this with d pi of S, d pi of S2, dot, d pi of Sn. Yes or no? Then only you'll get back this vector. This is a n cross n and this is d cross n. Yes? No problem.
Yeah.
So you will get is phi transpose d v pi minus phi w is equal to 0. So you get v pi v transpose phi d w minus phi transpose phi w equal to 0. W star is equal to phi transpose. Again, I forgot the d here. Phi transpose d phi inverse phi transpose dw. So again, this is what you end up getting. Now let's try to see the geometric interpretation of this. Okay. So now, geometrically speaking, what do you want to learn? You want to learn, this is your v pi vector, yes or no? What do you have given to you? You have a list of phi S1, phi S2, and phi Sn, yes or no? Correct? All these vectors are given to you. As Shoham was telling me, all I am doing is taking a linear combination of all these vectors, correct?
Do we need to find the best V pi in that space, in that plane?
Yes. All you need to do is you have to find the best v pi that minimizes the error is minimum. As I showed in the 2D plane in this. So this will be your phi w star. This is all what we are doing. So we are taking a linear combination using these basis vectors that is given to us. These basis vectors in terms of phi 1, phi S1 dot phi Sn. And all we are doing is W1 phi S1, W2 phi S2. This is what Shoham was telling me initially. Wn phi Sn. And this is going to give me phi times W star. And that is the best approximation of v pi on the column space of phi. If you're not following this, this is okay. You can always learn a little bit of linear algebra and then it will just be easy. Okay. That is
right.
If we know the linear algebra, it becomes really easy. We don't need to do the multiple differentiations again and again.
Correct. You can just project it.
Use the projection matrix formula and
yeah,
it becomes so much.
Yeah, correct. But we could do the projection and then we would not know how to do matrix calculus. That's the sides of the coin. You can always project it into this using orthogonal vectors and do it. That's what is there in the Gilbert Strang book and his course everywhere. And then that would be a bit of a we would not learn the vector calculus. That's the idea. Anyways.
Are all the phi's independent? You said basis, so I wanted to ask. We are sure, right? that all of
It
them
doesn't really matter. Like I didn't mean to be basis vectors, but yeah, it need not be independent. But then they are just they span the okay. They're not basis. Sorry, thank you. They're not basis. They span the column set. Span the column space. Okay. I was just being a bit sloppy, but they'll still have a minimal set, which would be a basis set, right?
Yeah, got
Okay.
it. Yeah.
It doesn't really matter because even if they are dependent, they will just W will learn it accordingly. Okay, this is one. And the other one is, so this is your normal error term, V pi, you are minimizing the L2 loss. But the other loss that I have here is V pi minus W V pi minus PW into D. Correct? This is the other loss. This is also known as the norm induced by a diagonal matrix. So this is induced by D. So this is not basically, see here, it's not exactly this matrix that we are having. Instead, we're having a shifted vector, right? This is the geometric representation of WMSE. WMSE, weighted MSE, right? So this is your just MSE, and this is phi WMSE. Is this clear? So this will be just some other translation of the basis vectors. That's all. That's all. Because what you're seeing is you're just multiplying the D matrix, which is increasing some vectors and decreasing some vectors. That's all it is doing. So this will give you another vector in some other which minimizes the norm with the diagonal matrix. That's it. Is the intuition clear? They'll not be the same is what I'm trying to say. Yeah. They'll be stretched out by this diagonal matrix and they'll be rotated a bit because of the diagonal matrix also present in the inner of the inverse matrix. Okay. So now, as we saw in the first few classes, we did what is called as the gradient Monte Carlo. We didn't do gradient based stuff, but we did something called as the gradient descent, right? So we learned that if we have a function like this, I showed it that if this function is a function of W, I can get WT plus 1 as WT minus alpha times DL dW at W equal to WT. And I said that using this learning rate, I could basically roll down this incline and go to the minima. This is called the gradient descent algorithm. And we proved this using the Taylor series, that what happens is f of WT plus 1 is less than f of WT. And we keep on decreasing for all t. So all we want to do is see for the till this time being, we were learning based on what? We were learning a closed form solution. Yes or no? Do you agree?
Yeah.
But now we may not have a closed form solution. Inverse may not exist. Many things could happen. So inverse may not exist. May not exist. We may decide on a neural network to give us what do you say, the value function?
Could we use pseudo inverse?
Yeah, you can use pseudo inverse, but that's only for linear function approximations. And also these matrices could be very large in themselves, and even the state space could not be finite. So all those things could have happened, and therefore we need some approximation methods to deal with that. So you can always use pseudo inverse, Penrose inverse. But here, what we'll be doing is we will be trying to do what is it called? A numerical approximation of this W, which is a optimization algorithm called as gradient descent. So we will take the derivative at that point and we'll just use physics and try to roll along the gradient. That's all we'll be doing and reaching this stable equilibrium point. That's all in this algorithm. We have shown the proof in the past. So now the same algorithm can be used now. The main idea of this is to introduce to you something called a stochastic gradient descent, but which will be using next day. But now if I have to use this xt plus 1, this gradient descent algorithm, I can now use it very easily. Can you tell me why? So see, now this does not depend. This does not depend. I'll write it down. Does not have to be a linear approximation algorithm. Do you agree? Does it have to be linear approximation? Does not, because we do not want closed form. We want a iterative approach. So let us take the derivative of this error function with respect to W. Tell me, what will this be? So say this is half. So this will be minus. And what will I multiply with this? Can you tell me? The gradient of
FW.
yes or no? Yes, that's it. So see, this gradient was, as you saw in our case, was just phi transpose. But now if it is a neural network, you can do back propagation or just put phi transpose if it is required, isn't it? That's everything. All the flexibility now comes up to with us. Now what we can do is WT plus 1 can be iteratively written as WT plus, or rather minus, alpha times d epsilon dW, which is WT plus summation of S in S d pi of S V pi minus FW of S gradient of FW of Fs. Do you agree? Any questions? So again, see, you get another added advantage with this. We get the gradient, we'll write down the SGD, and we'll see what is an SGD and so on. We'll see what is gradient Monte Carlo. So again, this is the expected value of what? Minus of states sampled from d mu, V pi minus FW of S, gradient of FW of S. Yes or no? Correct? Yes or no? This is again the expected value with respect to this probability distribution d mu. Clear?
Yes.
Okay. So what I say is, in a SGD algorithm, we don't need to get over all the states. This is not required. We can just do a stochastic update. Whenever we have an expected value in gradient descent, we don't even need. This is called stochastic gradient descent. We'll prove it. Why? Gradient descent. Stochastic gradient descent, we don't even need the entire expectation. All we need to do is just write this. So we can write WT plus 1 as WT plus alpha times V pi of S minus FW of S. Just for one state we can update. Are you understanding? Just for one state. So as you traverse the Markov chain, ST plus 1, you can keep updating the W's using the stochastic gradients. Clear to all of you? So I'll tell you what is the case, but is the algorithm clear? Whatever is in the expectation, you can, since by law of large numbers, you can use it. Right?
And is the alpha fixed?
Alpha is fixed here. You can also use a schedule of alpha. Here, alpha can be fixed. You can use it as a hyperparameter and fix it. Small alpha enough. Gradient descent. There's a lot of theory of optimization, which can depends on Lipschitz smoothness and so on. But we're not going into those. That's a 1 semester course just on optimization. But for neural networks, for all practical purposes, people fix the alpha. Clear? To some small value. Alpha is basically the step size. So how much do you descend? Based on this, how much do you go? That's alpha, right? So you can always choose small values and hope to converge. That's how neural networks work. Mostly. Okay.
Yeah, could you just once more repeat the distinction between this and normal GD?
So in GD, you are taking this entire, the expectation is over all the states, right? Right?
Yeah.
But whenever we could write an expectation, I am saying whatever is in the expectation, I can put it for the update. I don't even need to take the expectation. I can take one step at a time and do the update instead of taking all the states, computing the gradients. Okay.
Okay.
Let's take an example and then we'll understand what is SGD. We'll do SGD at the end. Let's write down an algorithm to do this. So how do you think? So this is not known. So can you give me an idea how to do this? You can approximate it. So approximate it using Monte Carlo. That's why it's called a gradient Monte Carlo. You can write this as GT given ST equal to S. Yes or no? So what you do from state S, you start, you traverse till you reach the terminal state. You collect all the rewards, R1, R2, Rn, right? And then just add them and put it in VPy. Fine. Yes or no? Fine. Let's see how do you do it? Can you tell me as to a DP for t equal to t minus 1, t minus 2, ... 0? What can I do? I can write GT as GT plus 1 plus reward. Yes or no?
Yes, like we did in model free approaches.
Yes, we will just get this GT and then for every state, I will get a VPy of S, which is the summation, which is basically this GT. And then I will just update WT plus 1 as WT plus alpha times VPy of ST minus FW of ST into gradient of FST. Okay, this is all you need to do as the update. Fine. This is the DP. But now the math that I want you to take away from SGD is this. Why does SGD work? SGD work. Say you have a function f, which is a function over parameters w, and a data set x, I equal to 1 to n. Okay. So what does a data set mean? Again, this function will have different values, right? For all these data points, right? Whatever function you choose, wmx plus c, for example. Correct? We have all of these values corresponding to all the xi's. Yes or no? So you write the losses over all the terms as say some fw 1 by n fw xi. Correct? You have individually, you say that say xi yi minus w transpose xi squared, right? And you individually add them up. Yes or no? Fine. Let's write it as some other different function f. This is the total loss. Yes or no? Any questions? So I told that this is S V pi of S minus phi transpose S into W squared. Yes or no? And like this is one data point, right? One point. I have S such points or N such points. That's what I've written. I've written the summation. And I say that individually this is f of W comma S. Can I write this or not? Am I audible?
Yes, yes.
If you have a question, you can ask me. This is the last thing I'm doing. So now you see one thing. I equal to 1 to N if Wi if W xi. Okay, this is what I have written down. Now I say that I is sampled from uniform 1, 2, dot, 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 N. Okay. For example, clear? If I assume I is sampled from uniform 1 to N, do you agree that this can be written as the expected value of f of W comma xi, I being sampled from uniform 1 to N? Yes or no? 1 by N is the probability of selecting one number between 1 to N. It's probability of I equal to K or whatever. Sure.
Yes.
So this is just the expected value. So now my SGD, normally I would have written your updates as WT minus alpha times the gradient of F, which is WT minus alpha times the summation of 1 by N, the gradients of the individual functions. Yes or no? By linearity of derivatives, right? No problem. Okay. So now I say that this is your GD, but my SGD will be WT plus 1, WT minus alpha times gradient of f of W xj. J is sampled from uniform 0, 1 to N. So now why do I do this? I say that this is a random variable, right? This is not the total gradient. This is one of the gradients, which will be a random variable of the actual gradient. Yes or no? Let us see what does this mean. So if I take the expectation of the gradient of f W of xj, what will I get? Tell me. J is sampled from uniform 1 to dot 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 N. What will I get? Just tell me the lotus. 1 by N into the function value. J equal to 1 to N. Yes or no? So 1 by N. J equal to 1 to N. Gradient of FW of xj. So which is equal to the gradient of capital F. So which say this is called an unbiased estimator. Unbiased estimator. So in expectation, your gradients converge. In expectation, your gradients are equal to the total gradient of GD. Any questions before we go on to the implementation of the TD0 algorithm? Any questions? Okay. So the TD0 algorithm, what is the update rule? Do you remember for tabular case? V pi or Vn plus 1 of state S is Vn of S plus gamma of S.
Gamma
Yeah,
of
tell
S
me.
plus d of n of
Dn. Okay, Dn.
dsn.
Okay, DSN. Now tell me what is DSN?
Now dsn is the reward we obtained at state n. Yeah, SAS dash plus v of n of s dash
Okay,
minus
minus.
vn of s.
This is what we'll try to implement. Let's try to implement it. Stop sharing from my tab since you have no questions. Okay, so I'll share now. Can you see my screen? Can you see the screen?
Yes.
Okay, so what I'll do is I'll do a very simple thing. I have already discussed this environment with you all, and this is also in your assignment to discuss, do several things. So it's the same environment. I'm not going to into it. Just the diagram here. These red ones have a reward of -100. You fall off a cliff, basically, if you go into the red states. And we did policy iteration, policy improvement on these states. Okay, and we derived the loss, the optimal policy. We've also done Q learning. I'm just adding on to this. So, okay, so let's do a model free TD0 algorithm. So remember TD0 algorithm, as you can see, as n goes to infinity, Vn goes to V pi clearly. So I'll just open my notes on the right so that you can see. Okay, so I have the equation ready here in front of me. Okay, so now you see that for a V pi, we have written down the value function. That's all right. But what we know is Vn plus 1 is Vn plus some alpha, that is the schedule rate, plus reward from state S, A to S prime, plus, as you said, the next state's value function minus the previous states. And we saw that for a given policy pi, as n tends to infinity, Vn goes to V pi. Okay, so this is very similar class I wrote. So what did I say? Here, say if the policy is given to me, I select, I keep the policy fixed. If the policy is not given to me, I select a policy of, so here, this is the x coordinate of the grid world, this x coordinate of the grid world, this is the y coordinate of the grid world, and this is the actions that I can select, that is going up, down, left, right. I select a uniform policy if nothing is given. Okay, so now again reset and all this we can see. So basically what are we trying to do? We are trying to do TD learning. Say we have max iteration of 5,000. So say what we start doing is we say start. We tell the environment to start. So let's see what's the start function. In the start function, we set the current state, or we name the current state currently as previous state. We set it to the start state. That's what we have done over here. We set it to the start state and we take a action. So for the current state, you take an action. So let us see what's an action. How do you select an action? So it's an epsilon greedy selection of our action. So if it is less than some randomly, else you choose randomly from the valid actions. Is it clear to everyone? Epsilon greedy action selection. Greedy action selection that is less than epsilon. Select any action, else select randomly from equal probable actions, from equiprobable actions. The equiprobable actions is written here. So wherever it is 1, you select randomly from those locations. So np.where tells me where the value is 1. Okay, so now I select the action as well. So next, what it is telling? It's telling me to complete the trajectory for that state. So let's see how we complete this trajectory. So complete trajectory is here. So complete trajectory is basically you just select a step and see if it is completed or not. If it is completed, you go out of the loop. If it is not completed, you say that the current state is visited once. Clear to everyone? So the step function takes one step and returns if the agent has entered the terminal state or not. Okay. So now let us see what is the step function. In the step function, you tell the environment that I'm going to take a step. You observe the next state and the reward. If we'll come to this, if it is a terminal state, what we do. But if it is not a terminal state, what do? I compute delta t. Delta t is basically the reward I saw plus the learning rate, whatever gamma parameter here, it's 1. Next state value, this is S dash minus the previous state's value. That's what I wrote down, Vn plus 1, Vn S dash minus Vn S. Now, the update for the current state is plus the scheduler for the current state into delta t. Clear to everyone? And the scheduler is just seeing how many times the current state has been selected. So let us see how do we learn the schedulers. This is basically the number of times you visit the current state. That's all. Okay. So now when this condition is validated, that is, it is an end state, you get this delta t as that you don't get any other reward, that next reward is 0. Therefore, you just subtract the previous state's reward from the value function from the reward, and then just do the update, same update. And this is what continues. This is exactly the algorithm that I've written over here, implemented it over here. So let's see how it performs. So for a uniform policy over here, it does find out that these states are very, 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 very harmful. Just like we had found out in the real world example. This state is not good. That's what it found out. This is not a good state. These are not good states. These corners are not good states. Clear to everyone? If you follow a uniform policy. Now I select the optimal policy, which was selected by the TD learning algorithm. So this is the optimal policy. That is the agent P policy iteration algorithm. Say I got this. And now I see compute for this policy. So this is the policy. So the policy is given, again, recall for a TD learning algorithm. You know the policy beforehand, and now you compute the value function. So that's what now we are trying to compute the value function. This agent is moving around the environment. It computes 10,000 steps and tells me the optimal value function. That's what exactly we found in the optimal value function. Just see, this is the optimal value function. So TD learning algorithm by exploration is able to find out a very similar optimal value function. Okay, clear? Any question? And your homework, which will be a part of your assignment, would be implement a TD lambda algorithm and compare the convergence and so on. Any questions? Anything you want to ask? Am I audible? I can't see you.
Yes.
Okay. If you have heard and if you're okay with this, have a look at the code. Try to run it on yourself. I'll upload it, and then we'll you can also implement the next part of the assignments when that is ready. Okay. So if there are no more questions, I'll stop recording. If you do you have any questions? Okay. Stop recording. Thank you. Okay.